Okay, so the idea with this worksheet is that you already have attempted these 6 questions, and that we're going to work through the answers on them. So we'll both generate answers, but then talk about kind of some of the common situations the AP puts in place. So this first problem, they're giving us a generic expression, and they're saying it's a Taylor series about 0, or it's a Maclaurin series for which of the following. So the first 3 are the big 3: sine, cosine, and e to the x. And the AP expects that you have those under control. And e to the x is x to the n over n factorial. Sine is, well, actually cosine is probably a little easier to look at. That was the one we first started with in class. And that one looks like this. And then sine is the integral of cosine. So we're just going to make the power 1 bigger, and we're going to make the bottom 1 bigger for our factorial. So those are our 3, our sine, cosine, tangent, or sine, cosine, and e to the x. Those 3, they manipulate quite a bit. These other 2, this option D and option E, option D is just taking option C and making the x negative. And you can see that the one they've given us does not directly fit any of the 3 terms. So it's not sine, it's not cosine, and it's not e to the x. So it's either D or E. It's one of those 2. So we can rule out the major 3 right away because it doesn't match. And then ln of 1 plus x is actually one of the ones that it's kind of a lower percentage one, but they do expect that you have it under control. That one, depending on how you write it, looks an awful lot like the one that they've given us. And where it comes from is taking 1 over 1 minus x, where it equals x to the n. So that's our geometric that we first started this whole infinite series exploration with. And then it's taking the integral of both sides. If you integrate both sides of this, you get the negative ln of 1 minus x. I guess technically absolute value bars there. We integrate this side, we're going to get, that is a rough summation, x to the n plus 1 over n plus 1. And when we do that, we get something that does not have a factorial on the bottom. And so there is no factorial in that one, which allows us to toss out option E. The other alternative that I think most people would probably do on this one to pick D, which is the right answer, so e to the negative x, is you're going to take the most common one, which is the x to the n over n factorial, and you're going to sub in a negative x. Well, if you sub in a negative x into that, all you're doing is you're taking the generic expression and you're keeping it structurally the same, but you have a negative x in there. And then that can be separated out as negative 1 to the n, x to the n over n factorial. So that generates option D. So that ends up being our answer on that one, option D. For the next one, and actually I'll leave the sine one up here, they're asking that we just manipulate sine. So they're asking that we take this expression for sine and that we adjust it. And so in general, it's important to know the general one. In specific, sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. It looks like they go out to the 7th, so let's go to the 7th. 7 factorial, dot, dot, dot. And then we're going to divide each of those by t or by x. So we're just going to power them all down 1, but we still need this alternation. So right off the bat, not alternating, not alternating. The other ones are alternating. That first term needs to turn into a 1, which then leaves me just this option, option A. So we're just taking the generic structure for sine and we're dividing everything out by x, and that's really it. This is a sight recognition problem for sine. They're not asking you to recreate the actual Taylor series on this one, just to use the generic structure. Same true on e to the 3x. So e to the x is our summation x to the n over n factorial. Or another way to write that, 1 plus x squared over 2 factorial plus x cubed plus x cubed over, oh boy, that just got out of hand. Let's get the eraser going on that. There we go. Plus x cubed over 3 factorial. And that's where we're going. We want this term. and we want it for e to the 3x. So we're going to swap out the x and replace it with a 3x. That's not going to impact the power, but it will impact what the coefficient is. So if we take that term, every term, but we're only interested in that one, and we swap out the x with a 3x, we're going to end up with a 3 cubed up top, which is a 27, and we're going to end up with a 3 factorial on the bottom, which is a 6. So the coefficient for the x cubed term is 27/6, which obviously they've reduced it because that doesn't show up here. But if we divide the top and the bottom each by 3, we get 9/2, which is what the answer would be for the last one on the first page. So kind of two examples here back to back of what they expect you to know in general in order to pull an e to the x or a sine to the x. And then the first one is doing a manipulation and not getting sucked into a potential false answer with e. So these three are all templates for just kind of having to know what the generic structure looks like. Same to be said of the next one, sine of 2x, and you can kind of see a pattern here, hopefully. What they're doing is just doing a recognition problem of, do you know what sine is supposed to look like? So again, we've got that right here. So that's our x minus x cubed over 3 factorial, x to the 5th over 5 factorial. So x cubed over 3 factorial, x to the 5th over 5. I keep hitting that. There we go. Just make a big plus sign, x to the 5th over 5 factorial, and so on. Here we're going to do 2x. So we're going to take x out and replace it with 2x. In truth, the only two that actually do that are b and e, if we just simply look at the first term. So we're automatically down to those two, and then it's a matter of which one do we pick. The only difference between the two is the alternation. Sine needs to alternate, therefore the option is b, and so our answer on that should be b. So again, just taking the general template for sine and making an alteration. True of the next one as well. Taking the general template for sine and making an alteration. This one is a little trickier, and I'm going to keep up this expression up here. So this one's a little bit trickier in that they're asking for the coefficient of x to the 6th, which there is no x to the 6th term in regular sine, but they're expecting that you make the recognition that we're plugging in an x squared. So instead of x, we see x squared. Instead of x cubed over 3, we see x squared to the 3rd power over 3 factorial, and we see x squared to the 5th power over 5 factorial. So in this expansion, there is an x to the 6th term, and it's the second one. So the x to the 6th term has a negative out front, and it's got a 3 factorial on the bottom, which we just said was 6. And so that means our coefficient is going to be negative 1/6. So again, these all kind of fit a very similar mold in terms of the baseline knowledge that you're expected to know about the structure of these things. The last one I've chosen, the last multiple choice, deviates a little bit from that. So I'll switch colors. We're looking for a 3rd degree Taylor polynomial, not a generic one, not a general one, around x equals 2. You can see they all have the x minus 2 to the nth power, so that's not a separator in terms of what we're choosing. But what we're looking at is the function for 3 minus x. And again, what we want is coming up with some general form of a Taylor polynomial. If you have some way to memorize this, that's fine, but that's not what this one's after. What this one is after is just the generic structure, and we're going to be evaluating at 2. And again, they all have this component all over n factorial. And so what we need is a set of derivatives. We only need a handful of derivatives. We don't need a lot of them. But if we've got our function, and I wrote 3 minus x, I shouldn't have done that. I should write ln of 3 minus x. If we're going to take a derivative of that, so we're going to take a derivative of the ln of 3 minus x, our derivative would be negative 1 over 3 minus x. And our second derivative, let's see, second derivative, I'm going to rewrite that first derivative as a power. Just helps me to see it. So there's that first derivative written down as a power. That negative power is going to move out front. I've got a 1 rather out front, positive 1, and then I've got a 3 minus x on the inside. Drop the power by 1 when we take a derivative, multiply by the derivative of the inside. So that means my second derivative is going to be negative 1 over 3 minus x squared. And I can see right away that I've got this trend going on where my derivatives are negative. And that's going to keep happening because I'm going to multiply by this negative power, and then I'm going to do the derivative of the inside. So my derivatives are going to keep being negative values. And I'm going to evaluate them all at 2. So I'm going to take and plug in a 2. Well, the ln when 2 goes in, the ln of 3 minus 2, the ln of 3 minus 2, or the ln of 1, the ln of 1 is 0. So when 0 goes in, your function value at 2, so if I evaluate that function at 2, that's 0, which means there is no first term that's a non-zero first term. When I evaluate the first derivative at 2, I'm going to get a negative 1 over 1, so a negative 1. Evaluate the second derivative at 2, and I'm going to get a negative 1 over 1, so negative 1. And hopefully you can see the trend. If you need to take a third derivative, which we do here, you're just going to move the power out front, just like we did here. So we've got our second derivative. If we write it as a power structure, it looks like this. That power is going to move out front, so we'll have a 2 times 3 minus x, drop the power by 1, multiply by a negative 1, and that's going to be a negative. And we got a 2, we've got a 3 minus x cubed on the bottom. When we evaluate that, we're still going to get the negative. We're going to get the 1 on the bottom, but now we've got this 2 when we evaluate it. So it's still a negative. In truth, just kind of thinking big picture about this, all your derivatives are negative. Every one of them is generating a negative value. You wouldn't even have to do the analysis on this one to know that, yep, every derivative is generating a negative value. There's only one option up here where everything's negative. That being said, if we actually do this one to fidelity, we've got our 3 multipliers, our negative 1, our negative 1, and our negative 2. So if I set up my generic, that negative 1 is the first derivative, and that's getting paired with an x minus 2 to the first power, all over n factorial, which in this case would just be 1, so I'll leave that be. I've then got another negative 1, and I've got an x minus 2 squared, and I'm going to divide that by 2 factorial, which is just 2. I've then got a minus 2 times the x minus 2 cubed all over 3 factorial. And that actually is this final term, right? So that's this thing. 3 factorial is 1 times 2 times 3. So if I just look at that final term, I have 1 times 2 times 3 on the bottom. Those 2's cancel, and I'm left with just a 3 on the bottom. But again, in truth, from a sight recognition, the minute you see that these derivatives are all negative, and there's only one option up there that's all negative, you have your answer. So you can do it that way, or you can actually do the analysis all the way through and generate the 3 terms. And neither's wrong to do. It's just 2 different approaches to the problem.